How about Tom Brady? Now we're being recorded. All right, so welcome. Those of you who just joined, here's the background for the day. That is Bertha. All right. I always thought that commonly the name for this image is Bertha commonly. I always thought it should be Annie because there's a song, Annie laid her head down in the roses. Like, why isn't this Annie? But I always get yelled at when I say that. So it's Bertha, just Bertha. All right, so functions, again, they're identical across all the languages, unless you're in a language that's like based on Smalltalk or something, or Lisp, that uses kind of a list kind of format. They're all gonna look identical. So we're not gonna dig deep into functions because you have already seen functions. We're just gonna talk about what they look like in C in terms of how we need to treat them, because it's a little bit different. So here's a function, for example. This one's called adder. And let's actually go and create a new project. Close this one. Let's create a new one. Yeah, terminate it. And we'll call it a new project, and it's going to be a C executable. And let's call it functions2, maybe. I think that's all we need. Create. Off we go. It's created. Blip, blip, blip. Looks like it's uploaded to the container. And here's our project files. Let's just make sure it runs. Hello world. It does, in fact, run. So let's create a function here. And let's call it, I want to use this function. Let's call it adder. Is that the one over here? Yeah, sweet. So it's going to return a float. We're going to call this thing adder. And it's going to take two floats as arguments. Float, left, and float right. And I'm going to create an intermediate variable here. Normally, we would just return the sum of these two because I'm going to add these two things together. I'm going to create a result variable just because I want to show you something later on. So float result equals left plus right. Ri, thank you. And then we'll just return that. Return result. Yep. All right, there's our function. And let's use it up here. So I want to say something like float result equals adder, and we'll pass it like 123.4 and 567.8, and we'll print that out. F result is going to be a float %f comma result. Oopsies. Bip and bip. All right, sweet. Result. It's a Swedish spelling. All right, let's compile this. So we'll do a build on it. Oh, no. Scanning dependencies in function main, implicit declaration of adder here on that result. So here, I've like conflicting types. There's all sorts of stuff going on here, right? Not good. So it doesn't compile. The big reason it's not, there's several reasons why this isn't compiling. One of the big reasons is, remember what the compiler does. Like one of its main features is that it looks at what you're doing, it compares it to what you said you were going to do, and it makes sure that you are doing what you said you were going to do. For example, if I say something as a float, and later on I use it as a string or something, or an int, the compiler will stop dead in its tracks and say, wait a minute, you said that was a float. That sure as hell looks like an int. Which is it? And it won't even compile the program. This, it eliminates a lot of runtime errors that were based on insufficient logic in our programs. But it needs that information. It needs to see what our intent was so that it can do the checking. Was it a float? I don't know. I got to tell it was a float, right? So what's really missing here is, I mentioned it on our last lecture, I think. Was a question, you need to say the function exists before the main function. Yeah, actually it's before I use it. Before I use that function, adder, Let me make this a little bit bigger for you. Preferences, tool chains, editor, font. Let's make it like 20. A little easier to see. Is it cool for you guys to see the the dark mode up here? Is you want light instead? Dark's cool. Just glare, you know. You would think they would have this fixed, but a lot of glare. Light attracts bugs. Bernard, that's awesome. That's the funniest thing I've heard all day, man. That's awesome. Okay, so yeah, so we just need the prototype. We need to tell C what the intent is, what it should look like before we first use it. And so what we really need here is just the prototype for this adder function, right? It's nothing fancy, it's just the type. There's no implementation, it's just the type information, and C's gonna check it for us. So the prototype for that thing looks like float, adder, float, float. C-line does a really nice thing for us. I can just right click on this, show context actions, or I can just do if you're on a Mac, you can do option return. It's probably alt return on a Windows box. It's like, oh, one of us is, I can split the function into a declaration and a definition, which is exactly what we need to do. And so it does that for us. One thing it does is that I don't like, that's probably a way to adjust this. I don't really need the names of the variables here. It's just the shape. What's the shape of the function? It's two floats, like that. So now I got float adder, blah, 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 blah. And let's see if this works. Build. No, you can't. Why didn't it build this time? Anyone know? I put a prototype in.
You need to put it before the main function because you're using it in the main function, right?
Yes, and yes. It's first use. So the files are compiled top to bottom. I've got the prototype down here. I really need it up here on line 2 because I'm going to use it here. I need to know what the shape is so the compiler can do the test for me to make sure I'm using it correctly. So I'm just going to take that out and stick it up here like that. Now let's see if she works. Ooh, much better. Much more better, right? And by the way, somebody asked about this in A1, so I'll just mention it here. Like the question was, what's this format and left and right and so on? That's just C-line being friendly. So it's reminding me that, oh, in printf, that first argument is the format argument. And then here it's saying, oh, in adder, I've got 2 arguments. One of them is called left and one of them is called right. And I'm going to pass those over. So it's that's just the IDE being useful for us. Can we get rid of what, Jonas? The hints, like IntelliJ?
Yeah.
Oh, yeah.
Thing.
You find it annoying? I actually like it, so I've never turned it off. I'm sure there's a way to turn it off. It's probably, if you go into preferences and search for IntelliSense or something, Intelli something, it'll probably show you what to turn off. Yeah, the IDE is extremely configurable. You can make it do just about anything you want. Hey, Jonas, if you figured it out, let me know, or just post it on Piazza or something. All right, so that worked pretty good, huh? Did it run? Let's run it. Result is some large number. Sweet. It's a little bit ugly, I guess. Let's talk about that prototype. So where does it go? Where does the prototype go? The rule of thumb is you need to see the prototype before the first time you use that thing. So in this case, we've got, here's the prototype. It's the second line of code, right? And I use it here. If I stuck it somewhere else, in fact, we did stick it somewhere else and it didn't work because I tried to use adder here. And when the prototype was down here on line 10 or 11, it's like, I haven't seen it. I can't check it for you. But now it's up here, that's fine. So generally speaking, prototypes go at the top. I think technically you can put them anywhere in the code as long as it's before the first time you use that thing. But like, it makes sense, I think, to put them at the top because that's where all the include statements go. And really what we're doing here is an include. Was that a question or just somebody yawning? Just somebody yawning. So that the prototypes go at the top, generally speaking. Again, they don't have to, it's just before the first use, but just sort of by convention, they go up at the top. Let's say I've got 100 of these. Let's go back to the code. I've got a whole bunch of functions, all types of math functions and so on. They're all listed down here. I got a whole bunch of prototypes up at the top. Organizationally, that gets really messy really quickly. And so instead, what we tend to do is we take all that prototype information and pull it off into its own file. In C and C++, that's called a header file, .h. Other languages don't have that. In fact, when the Java design folks, started working on Java, the language, they were kind of moving from C++ into, they were trying to build, well, originally they were trying to build a language that ran toasters, but eventually they realized, oh, we need kind of an enterprise kind of language that's similar to C++. They wanted to take out the top things in C++ and C that screwed developers up. The very first thing, no header files. The second thing, no pointers. I don't know why pointers are such a mystery. We're going to talk about them on Thursday. You'll find out a pointer is just another variable, really. But they eliminated them they hid them in Java. They're still there. They're called references instead, but it's still a pointer. But you don't have access to them really, the way you do in C or C++. How does prototyping work with recursion? Olivia, that's a really good question. We're going to get to that in just a sec. Actually, not directly into recursion, but you'll see a way to fix that sort of problem. Because watch what happens. We tried to make this break in A1. It wouldn't. It won't. I don't think it'll break again. Yeah, it still builds. I mean, if I did this, of course it would break. That's breaking, right? Because I have conflicting types. Normally, and this is, I think this might be the ID, like stepping in and helping us out. Actually, somebody mentioned in A1 that maybe it's a feature of the language, like a new feature in the language that's fairly recent. The issue is that normally when you have that twice, so if I do that and somewhere I've got another one of them, that's typically an error. I mean, in this case, they're the same, so maybe that's why. I still think it should be an error. Like, you guys got to remember, when I was coding like seriously in C, it was the 1970s, and so most of my skill set in C is pretty old. So if there was like a recent addition to the language, like 5 or 6 years ago, I walked away from C a long time ago, and so I haven't seen those new things. Like, if as they come up, I'll try to like figure it out. Oh, that's a new feature. Matthew says, is that not called function overwriting? I've never heard that term. Do you mean overloading? They might mean an overload. Anyway, yeah, overloading, right? I'm not going to worry about it. Let's make sure it builds still. Nice. All right, so this still builds. But again, like, what if you have a whole bunch of these, a whole bunch of prototypes up here? I've got all these implementations down here. Like, that's not really what this is about, right? This is this is the logic, the business logic of the program. This is what the program is doing. These are all just things it's using to do that. And so organizationally, it doesn't make sense to have them all together. For several reasons, it makes sense to pull them apart into their own separate files. And that's exactly what we're going to do. So normally, we're going to put those things, the prototypes go into a header file, a .h file. And then we're just going to include that .h file. So just like you've used standard IO, right? So this includes standard IO.h. Standard IO.h is just a header file. What's in it? A whole bunch of prototypes. Let's go take a quick look. Do I still have a connection to my container here? I do. Where is standard IO.h? It's over there. Let's go there. Less. user include standard IO. Here's standard IO.h. It's a header file. It's just got, let's look for printf. So there's the printf stuff. And you'll see, like, these are just, those are prototypes, right? So that's where all the prototypes live in this header file. When we want to use standard IO, we include its header file. Same thing we're going to do here with this. I'm going to take this information and actually I'm going to create a new file. Let's do new, make it a little bigger for you guys. New C or C++ source file. And we're going to call it, let's call it maths. And I want both. I want, so this says, oh, I'll give you the .c file. I'm going to click on create an associated header also. That'll create both files for me automatically. So the name is going to be, the two files are maths.c and maths.h. When I create it, click OK, off we go. And now I've got maths.c and maths.h. Let's go put the implementation in the C file. It's like interface. You know, I don't think that's it, Arnav. I don't think that's what it is either. I'll have to, like, I guess I gotta read the spec, huh, and see why it does that. Let me go put the implementation over here. That was the implementation of this function, adder. Cut it. It's going to go in maths.c. And let us go over to maths.h. The header file is where the prototype goes. And where's our prototype? It is right here. Cut that out. Notice that this just went red, right? Oh, what is that? I don't know. Oh no. Well, let's go put it over here. Maths.h. That prototype goes here. We'll find out what these if not defs are in a sec. And then finally, like, I still can't figure out what the heck I mean by adder. What I really need is an include statement here. The IDE will do it for us. If you just hover, it says, oh, you screwed it up. I don't want a new function. What are my more actions? Can it find it? Here we go. Import the function from maths.h. So it does it for me, and really all it did was that. So it just included maths.h, the header file. It's exactly the same thing as having the prototype line there. It's just now that prototype is over in maths.h. We're including maths.h. Include essentially sticks that file right on that line. It's exactly the same position, basically. And now adder looks fine, right? Because I've included maths.h, and I can use adder. Let's take a look at the differences here. So notice that there's two formats for the include. If I'm using a standard library, and I don't mean std something, I mean like an installed library that was installed by GCC, by the system, they go in gangster brackets. So that standard io.h, this tells us it's a system header file. Header file, the Swedish spelling file. They go in a standard location on the file system. User include, in this case, for this container, sometimes they're in user local include, user / local / include. They can really be anywhere. Actually, those two are the typical spots for the system files, the installed stuff. And then the second one is this. So I've got this little quotes marks around math.h. Maths.h in quotes means that's a local header file. Local to the project, really to the compile path. So it's going to look for standard io.h in user include. It's going to look for maths.h in the directory that we're working in right now. If I happened to, like, maybe I created a, let's read that. I'll get to that in a sec. If I include, like, built another folder here, like, and called it headers or something, you have to give the path. So I would say headers, I should say here.headers, like that. So if I had that headers folder created, this gives it the full path to that header file. Here we don't have a directory. It's just sitting in the same level as all the other files, so we don't need path information. Actually, the path information is this directory, so we don't need that stuff. The dot means here, current directory is dot, and then slash headers is be where we stuck that thing. Sister says, why do we not have to include the implementation as well? We'll actually get to that too. So that's coming up. I'll leave you to sit and anticipate that. At this point now, everything's going to compile. So we can actually compile, run this thing, off it goes, results 2. Why is the result 2? Why is the result 2? 123 and, oh, so I didn't actually, no, result. Really? Did I screw up a format somewhere? Result is a float. Huh, and it really does have, oops, I want to see here, variable. Let's go look at that in memory. It's not 2, it's some other number. I must have screwed up a format or something. I don't see what it is though. What's adder returning? Adder is returning result. Result is left plus right. That's a cool problem, huh? Let's rebuild it and see if it changes. Let's do it this way. It still says the result is 2. That is so weird. Did I just pick like really weird numbers or something? What happens if we change the numbers? Save that. Result is a %f, which is a float. So let's just run that one. So we get 18.2. Like that makes sense, right? We didn't like that was not over a float or anything. Those are small numbers. I don't know why that was 2. Huh. Does float have a default sig figure setting? I don't think so. Maybe it does. Yeah, maybe that was the issue. I didn't tell it how many digits to use, and it maybe used, that must be it. So the %f format, you can see this on page 555 of the book. %f must have a default value for the number of digits you're going to show, and it must be small. In fact, let's try that. 3.456, and then was 5.67.8, something like that, right? So let's see if that, let's take the debug off. Ah, that one worked. F you. I don't know why. Must have been something in cache or something. That's the answer to everything, right? I was in cache. You know? No, he's like, no. Somebody in the back had their hand like this. I thought you were going to raise your hands like, oh, he knows. He's like, no, I don't know. Aaron, I'm guessing you might be right. That %f probably needed a significant digits modifier. Welcome to C, ladies and gentlemen. Like sometimes stuff happens and you're like, why did that happen? You're like, I don't know. And then you do it again and it's different. I guess I picked great numbers. All right, so that's, anyway, back to this, like that's the difference, right? So if it's got quotes around the header file, it's a local header file. It's gonna be in my project, basically. If it's got gangster brackets, then it's a system header file. It's gonna be out on a Unix box, it's gonna be in user include or use a local include. There's a series of directories by default that the compiler is gonna look in those locations for those system header files. All right, so cool. Shout out the gangster brackets. All right, so let's talk about these things. Like, what's that about? Somebody asked this earlier, and I apologize, I don't remember who you are. Let's talk about these. Well, not that, with this one. Let's go look at math.h. So notice that when C-Line created this file for me, it did this. It created these things, right? These defines and endifs and so on. Here's what's happening. In some versions of the compiler, And I'm saying some versions because apparently there are differences. In many versions, most of the versions of the compiler I've seen, if I do this twice, I'm going to get a redefinition error. The C++ compiler for sure will give you a redefinition error for that. I'm not sure why this compiler is not. It's probably because the compiler itself has a number of switches, like 100 of them, to configure the way the compiler is going to work and what it's looking for and what it warns you about. My guess is that I don't have the switch turned on to warn me about redefinitions. That's probably why I'm not seeing the redefinition errors. They're there, it's just I'm not being warned about them. And apparently the compiler is kind of gracefully handling it, so it still compiles. I should see warnings for that though. I should turn the warnings on and see if that helps. We'll do that later. All right, let's talk about these. I don't want to see this twice. And remember how includes work. If I have an include statement in a file, it essentially grabs the included file and sticks it into that location in the source code. So over here in main, when I do include mass.h, it actually takes the stuff in mass.h and just sticks it right here before it does the top to bottom compile. That's a preprocessor directive. The preprocessor kind of goes through the files, does things like that. It expands macros that you may have defined. It includes all the stuff that you said you wanted to include. And then the compiler takes over from the top and goes top to bottom. But look at this. Here's maths.c. I have it here too. I need it in both places. I need the include in both places because at some point, the compiler is going to need to see that prototype. It for sure is going to need to see it there. It also needs to see it here because I'm using it. It's going to do type checking for me. And so I'm actually including it twice. I'm including it here, and I'm including it there. There. Pop back, thank you. Let's make that a little smaller. I want to avoid the redefinition error. To do that, I'm going to put an if statement around the header file, the prototypes. Here's mass.h again. What's happening here is when the preprocessor looks at this, it sees this line. It says, if not defined. If this thing is not defined in the system, in the compile system, define it. If it is defined, if it's already been defined, that's going to fail, right? It's just an if statement. So if it's not defined, go do this stuff. If it is defined, just go down to the end and skip all of that. In fact, let me indent this. Oops. Shoot, see. Why is it doing that for me? Indent, make it even clearer. So that's a big if statement. The first time through this, the first time I see an include of this file is functions to underscore mass underscore h defined? No. And so it's going to define it, and then that's the prototype that gets stuck into wherever I include it. The second time I do the include, is it defined? Yeah, it was defined the first time I saw it. And so I'm just going to skip it all. And so I'd never see that twice. If I include this 100 times, the first time that we see it in the compile, it's going to define it and then do that. And the other 99 times, it's going to skip it. So I only see it once. Where did it come up with the name functions to mass under h? Great question, Bernard. And Olivia, I'll get to your question in a sec. It just made it up. And if we look at the project, so the project is called functions2. That's where the functions2 came from. Maths is the name of the file itself, and it happens to be the header file for it. So it's the project name, the name of the file, and the extension is how it created that. It just built it for us automatically. If you're in some other, if you're in VS Code, for example, I don't think it does it for you. You'd have to write those yourself. And Olivia asked, can I reuse header files for multiple different files? Typically, a header file is associated with a source code file. So I've got maths.c and maths.h, they're a unit. And if I need another set of bunch of functions to do something else, like I'm doing geospatial stuff or something, I'll have another file like geospatial.c. I'll have geospatial.h to go with it. So that they come in pairs. Do you need to do it yourself, Dev says? Okay. Yeah, they come in pairs. All right, everyone clear on what the if not def does? Yeah, actually, let's go back and take a look at this puppy. Remember this guy? Let's go back to the top. There you go. There's standard IO.h. If not def standard IO.h, define it. And then you'll see like all of these things that start with a pound sign, hashtag, those are all preprocessor directives. These are the first things that happen before the compile actually starts. So we go through, preprocess the files, do all of these pound sign things. Sometimes they're defining things, sometimes they're including things. There's tons of them, right? Just tons and tons and tons. And then once all those are expanded, then the compiler hits. All right. Let us continue. So if does we just talked about. And that's the explanation for that. That's the explanation for built-in and locals. So you guys have the advantage of I literally just gave this exact lecture like 45 minutes ago. And so I can just go with the flow and not have to refer to the slides. I suppose I should refer to them. All right, now just as Olivia mentioned, I think that's where you were heading, like, can I reuse them? Usually not. So they usually are directly tied to each other. There are just two files. In fact, they end up looking like this. So here's kind of the representation. This is what we were just doing, right? So there's main, and I also have the header file for functions, maths in this case. And then here is the implementation file for it. That's the .c file. So .h on the left, .c on the right. So you end up with a pair of files for basically every module that you're building. And normally, like when do I know I need to create, one of these things? Usually what happens is like main typically is, that's the business logic. That's the thing that the program is trying to do. It's using all these other pieces to do it. And so main tends to be really, really short in most cases. In fact, I've seen mains where, main is just 5 lines. Each one calls a function from somewhere, and each of those functions does some significant amount of work. But really, main is just launching those functions one after the other. That's all it does. Anytime I've got a group of things, functions typically, but maybe definitions or something, that kind of go together. Like here, I've got this maths library. Maybe I'll put, addition, subtraction, modulo, maybe some spherical math, trig or whatever. I can put all those things in that library and then refer to them later on in my programs. So we group like things together. Do we need a file with main function at all? Sergey, you do. So by default, C is going to start with a function called main. It's going to look for main. If it doesn't find it, in fact, here's what it looks like. Let's call this not main. So I've got not main here. Let's try to build it and see what happens. It's like, yeah, I don't think so. Like I have no idea what we're talking about. Where's main is essentially what that says. So you actually do need, it's the same as in Java. What's the mantra in Java? I can't remember what it is. But like that long thing with argc and all that crap in Java. It's the one you just your fingers know how to type that particular start function. Does main always have to return an int? Well, if you said it's going to return an int, it better return an int. It needs to return an int. Here I'm returning an int. If you fail to do, if I forget that, or if I comment it out, it actually sticks one in and returns it for me, returns a 0. Oh, and by the way, last week there was a question about like true and false and returning a 0 here. So 0 is false and 1 is true. But here I'm returning a 0 to like indicate whether the program successfully ran or not, it has to do with the way the system defines its error messages. A non-zero return value from this running program is an error. A zero return value means it was a success. So it's really, it's not a C thing. It's not true or false in C. It's that the system itself defines how it looks at return values. If it's non-zero, there was an error. And so to indicate success, we just return a zero. If there is an error, like that, I could say, oh, I return a 1, that'll trigger an error message on, actually, wonder if it will. Will it return something? Well, it just says exit code 1. So that exit code is really this guy, right? If I say 999, 1999, I don't know why I did that. Now I get it returned with an error code of 207. That's an octal number, I think. All right. Where do we use that? Yeah, go ahead. We'll get to that. The question was, how does main even know what the implementation of adder is? Because it's all it's really including is the header file. There's no implementation in the header file. Like how does it even know what that code should be? That's coming up in a slide or two. Oh, just to finish this thought. So let me go back to like this 1 here, return a 1. So thank you very much. Let's rebuild that. So I'm returning with that code of 1 here. Normally where this is used is in scripts, S-C-R-I-P-T-S. It's hard to talk through a mask. So if I'm scripting something, like I'm writing a bash script to run a bunch of stuff, maybe in a tool chain or a sequence of events of some sort, I need to look at whether from bash, from the script, I need to know whether the program that I just called returned successfully or not. And so I'll watch that return value because that exit code of 1 gets returned to the caller. In this case, where the caller is standard IO. It's the terminal. And so we get the exit code on the terminal. If I'm running this from a bash script, the caller is the bash script, and the bash script gets that 1 in return. And I can, from my bash script now, say, if blah, then success or not, and do it that way. You guys will be doing some bash scripting later on in the course. That'll be one of your labs. In fact, I shouldn't ask you to do that sort of thing, huh? And you'll notice that as I change the return code here, like it doesn't matter to the C program itself. It's just, that's what it's returning to the caller. That's all. To rebuild, and off we go. All right, nice stuff. So, and by the way, just an aside, guaranteed. In fact, I should just ask everyone for $1 the first time this bites them. I would be rich. What is Bitcoin at right now? 47. Nice. I had $12 and change left over a couple of years ago from a transaction, and I just left it in my wallet. It's up to $580 something now. It's like, I think it's a great return. I'm just gonna let it ride. I'm also I'm also now long on silver. And if you know, you know. I like silver. Oh, good. Yeah, so this will bite you. The header and the implementation files, those two files, they are not connected to each other in any sort of way. If I change something in one, like if I go over here to the implementation file and say, you know what, that's not a float anymore, it's an int. And you'll notice that's screwed up because mass.h says, oh, it's supposed to be a float, right? It's still float over here. This won't build. Why? Because I changed something in the implementation file, which is where we normally work. We're normally coding, right? And so it's just so common to be coding away. It's late at night. You change a bunch of shit in the implementation, and you forget to change it in the header file, and then you're 100 files deep into an error message trying to figure out what went wrong. It's because, dope, you didn't change it in the other side. And I'm guessing, I'm just literally just guessing that CLion has a plugin that'll match those up for you. And if you change it in the implementation, it'll automatically change it in the header file. I'll have to look for that one because that is something that bites us over and over and over. That's like the first thing I ask, when somebody comes in with an error. It's like, oh, your header match your implementation? Oh, shoot. Can we just write one C file at all and not worry about it? Well, you could, Jaru, but like you guys, your code's probably going to be, the biggest stuff is going to be several hundred lines, right? Most like real programs written in C are hundreds of thousands of lines, millions of lines of, like literally millions of lines of code. You don't want that all in one file. And if I'm thinking organizationally, like I'm going to take the stuff that makes sense together, like the math stuff, and pull that off into its own header and implementation file, what I can do is I can compile that, get it all working, compile it, and then never touch it again. I've compiled it, I've tested it, it works great. Just never touch it, just include it anytime I need it. So functionally or organizationally, it makes sense to build up a program out of pieces that have already been tested, over time. And that way I don't have just, thousands or millions of lines of spaghetti code that I have to wade through all the time. I can go into individual tiny spots. Oh, I just realized there's a better way to do spherical, trigonometry. I'll go update my spherical trigonometry library, and then next time I use that in a program, I get the updated stuff. I don't have to go in and change it in the 9 different places that I had that code. So from a modularity standpoint, it makes all sorts of sense. And just like a sanity standpoint, it's like when something goes wrong and I see it was an adder, oh yeah, that's over in the math library. I gotta go fix that. Yeah, Jonas, you got it. It starts to get messy really fast, actually. Let me just fix this, right? Float. Oh, I wonder if it'll help me. I had an int there, right? Let's see if it'll help. What have I got? Previous declaration is here. Well, that's nice. So I can go there. Well, that's kind of cool, I guess. All right, sweet. So that's going to bite you for sure. All right, now we got a new problem. Yeah, we have a new problem. It was your question, which is, all right, so now I got math.c, I got main.c, like, which one's the executable? How do I even know what the executable is going to look like? Like, what's next, right? If I have 100 of these little files, these little implementation files, I got 100 of these things. Which one of them is the executable? There's another step we need. And it's actually done for us when we do a compile. There are like 7 or 8 different steps during a compile. We normally don't see them. They just happen. One of the steps is, actually we talked about a couple of them already. One of the first steps is the preprocessor. It's going to go look at all those hashtag things, hashtag include, hashtag define, all that stuff. That's not C, that's the preprocessor's language to set the files up the way we want them. Once that's done, we run the compiler. What the compiler spits out is actually assembly language. It spits out assembler code. That code's then run through an assembler. The assembler spits out object code, .o code. That object code is then linked together into an executable file. We just normally see, oh, build it, and oh, here's your executable, but all these steps are taking place, right? Olivia asks, do the file names of the corresponding .c and .h files have to match? No, they absolutely do not. However, if you name them different things, you're going to be in a world of hurt when you're 1,000 lines deep into your error messages and you say, oh, header, what header file was that in? Like the implementation, the header files are different. You're going to have to go figure out which one matches which. You could just look at the includes, I guess. But save yourself the pain and just name them the same. That could go on a t-shirt. Save yourself the pain, name them the same. So it's not a dumb question. There are no dumb questions in here. I should take that back. There are dumb questions. And by the way, I apologize. Like, I get pretty snarky sometimes, especially on Piazza. For example, when somebody asked a question, I said, read the effing manual. I didn't say it in those words, but that was what I meant. It's like, and where I'm coming from is like, this is college, guys, and you're supposed to figure it out. Like, I can tell you about stuff. Remember I said in the first lesson, like, I can't teach you to program. You got to do it yourself. Like, it's a skill. They have to do it to gain that skill. Go look stuff up and figure it out. Like, if you ask me a question, and especially that one, it's like, what's the, what was the format or whatever? It's like, it's literally in the book. Like, just go look in the book. So I get snarky that way sometimes. It's mainly just to push you guys to work a little harder, to figure it out. You got to figure it out, because when you get on the job, like, for God's sakes, if I were your manager and you kept coming to me, it's like, what's this format specifier? Like, it's you got Google, you got Stack Overflow, you got 9 books on your bookshelf, and you're asking me for that. Like, if you do that more than 2 or 3 times, I'm just gonna get rid of you. Like, you're a pain in the ass, right? You're wasting my time, basically. Go figure it out. Just go figure it out. This is, and you guys, it's college. For God's sakes, just go figure it out. Now, that said, like, we're throwing a bunch of shit at you, so of course we're gonna help you through that. But you know what I mean. I get a little testy sometimes. I don't play well with others, which is why I was a consultant, why I ran my own businesses, and why I'm a teacher. It's like, that's why. All right, so here's where we're going. Here's that situation. I've got main. Actually, this was it's called add. Let's call it mass, right? .c. It's going to change these so it matches. Mass.o. So I've got these things. I've got main. I've got math. They're both C files. They're both at equal standing, really, as they go through this process. So that's what this is showing. GCC is the compiler, and AS is the assembler. CC is the object, code. The compiler takes all of these C files, all the ones that are all linked together, and then creates object files from them, .o files. Those object files are really similar to Java's, I can't remember the name of their binary language in Java, but it's that intermediate sort of transportable language. You can move it from platform to platform, run inside the container, the Java runtime. Well, that's what these are. So these .o files for these platforms are like, I can move them around essentially. I can create that .o file from math.o. Maybe it's got some really cool math stuff in it. Build math.c, save math.o, and then just hand it out. And then you guys use math.o. You can link against it, is how we say it, without even having the source code. As long as you got the object code, you don't need the source file. It's already been built. That's what all those system libraries are. So if we go over and look, this is on, who am I? Oh, sweet, that's the container. So let's go over to user include, for example. Oh, I'm sorry, user.lib. What time is it? Do I have 15 minutes left? 3:15 is when we break. All right, so here's a bunch of stuff in user /lib, / long. All these things, right? So let's go into maybe yeah, let's go into GCC or something. I don't know. System D. Nice. I'm looking for shared objects. They should be in user lib. Modules, RPM, systems, OS releases, Java, games. Where are they here? Grub. Where is, let's go find the header file. It's in user include, so it really should be in user lib, huh? It's not user local lib, I don't think. Let's find it this way. So let's go to the top level. So I'll do a find from root, and the name I want is, I want standard IO something. I want lib. Let's do like lib G something star. So this is going to go to the top level of the file system at root. That's the slash. And I'm looking for anything that has libg as its beginning. So libg star will match all the files that have libg in the beginning of their name, and I'm going to print them. There we go. So let's go over like here, user lib64. There we go. See all these .sos and so on? These are all object files. In fact, if we pick one, how about libgc, since it's right there? Let's do files, libgc, .so, and I want, what, 32? Oh, it's file. Thank you. So if I do a file on that, it tells me what the file, it's actually, file just reads the file header, and in the header, it tells you what the file is. And so this happens to be, it's an ELF64 shared object. So it's a 64-bit shared object in ELF format. So what's ELF? ELF is somewhere down here. ELF is executable and linkable format. It's just a format for files. It defines what goes in the header of that file, how the bits are organized in the file, like what means what and where they go and so on. And you'll find ELFs in Unix-based systems, so Mac OS, Linux, Solaris, RISC-based Unix systems. I actually don't know what they're called on Windows. It's probably some other format on Windows. In Windows, you'll find these as DLLs, dynamically linked libraries, probably. But that's what's in there. So all of these things are just object files. The way these were created, there's source code behind this. We don't need the source code. All you need is the object that's been compiled successfully and the header file. You need the header file if you're going to use stuff that's in that object, because the types have to match and everything. So the compiler needs that type information, but I don't need the source file at all. I just need the object file, because it's the linker that's going to take all these object files. And in this case, I've got stuff I wrote, main.o, mass.o, standard, lib.o or standard io dot whatever, .o is going to be in there as well. It's going to be a .so shared object. And it's going to link all those guys together into an executable file that's one piece.
May I ask
So
a
the
question here?
linker does all that work for us. So
May I
the
ask
object file is real. Yeah, question.
Sorry, yeah. Could you go back one slide? So here, when you have like the header files, right? We include them at the top of the main.c in the main.c file usually. So in the main.o, then if we kind of like execute, so to say, kind of that main.o file, then it automatically looks for the other object files that it kind of identifies in the include statements. Is that how it works then? And that's kind of how the linker executable thing then works?
Yeah, roughly. So the question is around the include statements and so on, and how that relates to the object file. Once I get to an object file, those include statements, we're kind of done with them, at least at that point in the compile. So once I get down to an object file, I've already compiled that file, including all the include statements. This process is it's basically creating a table of symbols. So all of the function names, variable names, all those things get placed into a symbol table in the object. And then as I use those things, especially as I link them together, I know where each of those things lives in the object file because of the symbol table that's created. And when I combine them together in the linker, it's just going and reaching into those object files and mapping those locations in the object file into the executable file. So it knows that, oh, in mass.o, line 472 is adder dot whatever, the adder function. And so in the executable, it knows that when it links them together, it's actually going to have to relocate that. It's going to move it to another location, but it knows where to go find it first because of that old table. And that relocates it to another spot in the executable and then updates the symbol table in the executable itself. So I've got basically tables that keep track of all of the pieces, where they live in these files. And then as I link them together with the linker, I pick those pieces out, move them to a new place in the executable, and then create a new symbol table for the executable. So once I get to that point, the header files, really, I just need the header file if I'm going to use that object file somewhere else. In this case, I'm going to go through the linker, create an executable, but I can stop right here. I can stop at this level and just save off the O file. And now it's just kind of a library file. In fact, probably Thursday we'll build a library and you'll see like, oh, that's a library file now. It's a .o of some sort, and we can see where the headers and so are in it.
Right.
Wasn't a great answer to the question, but yeah, go ahead.
So it's kind of the locations are saved in the symbol table that you talked about, right? And then to the symbol table, the linker knows where to find stuff and then put stuff, and then it can put stuff wherever it wants, right? But is the symbol table then stored in the output in the object files, or where does the symbol table come from, or where is it kind of how does it operate, or where does it come from? Yeah.
So up on the screen is the file format for an ELF file. We'll actually dig into this relatively deeply at some point. But for now, I just wanted to kind of show you roughly how things are put together. So this is the ELF object file format. So there's a header at the top, right? And then I've got stuff for like here, where my jump table. So if I've got functions that I'm using in that object file, where do they live? There's a little table that keeps track of what address in that file that function is at. So when I refer to it, it looks in the table and knows, oh, I can jump to that address and start executing that function. Here's the bottom part of that file. So this stuff there's the header table, basically the section header table that tells me where all these pieces are. And then within each piece, here's the relocation stuff for, here it is. There's my symbol table. It's up in the sim tab section. So that's going to be all, it says procedure here. That's a function, basically. So within that object file, there's all the compiled stuff that's, I can link to, but there's also all this other information about it. And just like for completeness, this shows us down here at the bottom, so here and here, the purple and yellow, that is the ELF format. That's basically the code that we're going to run. All the other stuff this is created by the operating system for us when we start up a file. I'm going to execute something. It allocates all this stuff for us. And again, you guys are going to get sick of this diagram because we'll be deep in this one too, especially when we start looking at memory allocation. But this part down here, that's the ELF file. Everything else is, I'm going to create a stack for you. Here's a heap for you. Here's where this goes and so on. But most of the stuff in the executables in the ELF file at the bottom of that. That's address 0 at the bottom. And I'm not going to spend a lot of time on that on these 3 pictures. I just want to kind of show you roughly where things sit. We'll dig into them later on. That's part of the fun of the course, I think.
Thank you.
Yeah, sure. Where do I want to go here? 8 minutes. All right. I need to jump into something else. I need to jump into, let's make sure we talked about this, step in linking, we talked about symbols, relocation we just talked about, ELF files we just looked at. All right, so here's our issue. We're back to this, right? We're back to this. Like what's the command essentially that does that for us? We need some compiler command that creates the executable out of all of these pieces. And frankly, the high level view of it is we're just going to tell the compiler what the pieces are, and then it combines them for us. Unfortunately, there's something called a make file. Here's actually I can show you one in CLN, it's easier to see. Where's my make file? Here's the make file for this project. It's a couple hundred lines long. It's longer than the code. This is a make file. And here you can see, actually, here's make all. So make all, this just says, I'm going to take each piece, main.c, maths.c, and their associated headers and so on. It tells us which pieces we're going to use for the executable. Now, in previous iterations of this course, we've used make, and you've had to edit make files by hand. I don't like doing that. I think it's a pain in the ass. And so instead, we're using CMake in this class. And going forward, apparently, because this is my class going forward, CMake simplifies this a lot. The problem that we face is that make is different. The make file that we need is slightly different for each platform. So it looks different on Windows than it does on Linux. It looks different on Linux than it does on Mac OS. It looks different on Mac OS than it does Solaris and so on. They're all slightly different. So they're not really very portable is the issue. And so CMake builds make files for us out of this sort of thing. That's a lot easier to read, right? That's basically doing the same thing. This information in the CMake file, just like here's the executable stuff. We're going to call the executable functions to, and here are the pieces. Those are all the pieces you need. And in fact, when I didn't tell you when I did the new file, but let's do a new, I'm going to go over here to my folder, right click, new C++ source file, right here, add to targets. When I clicked add to targets, it added an entry for this file, maths in that case, maths.c and maths.h. Add to target says, oh, I'll go add that to your CMake file for you. So that's why maths shows up over here, is because we said, oh, include that in the target. So the target is the executable in this case, and I'm going to use these guys to do it. CMake now takes this information. The other stuff is really easy, right? The project is named functions2. It's in C. We're using C99 as the version for our C language. And then do the executable. It takes that information, it builds a make file out of that, and then runs the make file on this platform. So it's a platform independent way of defining make files. That it has its own language, of course, like everything else does, but it's relatively easier to use than make certainly is. If I forget one, like, the build won't work because I need, for example, maths.h, right? If I try to build it this way, save it, reload my changes, and then try to build this sucker, it's gonna wait till it syncs. Like it won't build because now it doesn't have the math header file, doesn't know how to type check that stuff. So I need maths.h here. Reload them. And by the way, there's a way, like anytime I change this file, it needs to rebuild the make file. So that's what this reload changes things is. And I just been clicking it every time I change something just to show you that I have to rebuild the make file. You can also, if you want to, enable auto reload. So anytime you change this file, it just rebuilds the make file automatically for you. It's a little easier that way. All right, so that's how we're going to build projects. And that's what invokes the linker, basically. We haven't told it that we want to like stop at any point. You can stop anywhere you want. Let me just see if I can set, what the devil is it? It's, I just can't remember the actual, let's see if it works. Let's see how my memory is. Let's see if that works. I probably forgot the syntax. Let's see, will it build? Yeah, it won't build. I didn't resync. What happened here? Build failed. S.H. I just need to rebuild everything, right? Let's do a quick resync. Tools, CMake. I'm just gonna reset the cache. And down here, you can see it's reloading stuff. It's rebuilding the make file. It killed cache. So CMake generates executables for us, correct? Actually, no, Jonas. It's still the compiler generating the executable. CMake generates a make file. Make file is used by the compiler to tell you how to make the project, and it's still the compiler that's doing the work for you. Yeah, it's that syntax. I can't recall quite what that syntax is. Sorry, guys. I'll look up that that syntax and we'll do it on Thursday. I just wanted to show you the .o files and so on. And I'm running out of time, unfortunately. All right, so that's CMake. Here is like roughly what it does, right? Rich language, et cetera, et cetera. And there's docs for it. Generally speaking, like our interaction with CMake is going to be pretty minimal. As you add files to your project, it'll throw them in here for you. And there's not really much else we need to do for our work. If we're doing more complex stuff, like we're using threads or something, we'd have a lot more arguments for the compiler. But our stuff is simple enough that we can just really do add executable, list the pieces, and it'll do the right thing. Dev says, when compiling, does the order in which you compile the files matter? It shouldn't, because it compiles everything separately, then it links them all together. They all have symbol tables so that you can find stuff in all the different pieces. So it should not matter which order you compile in. Jonas says, makefile does what? The makefile is the definition of how to build the project. All right, cool. One more slide. Bottom line. So the bottom line, functions are just like every other language. And it's why I didn't go into functions like, oh, this is a function, because you should have seen it at least twice already. But we do have separate definition and implementation files, .h and .c. When we do these, when you actually do the compile, it's a multiple step process. The first thing that comes out is a bunch of assembly language code. The assembler is, that now gets translated into object files. Then those object files are linked together and so on. Can I really quickly, do I have like 1 minute here? Let's see if I can show you the, let me just rebuild this. Did I have something up? Float. Oh, that's fine. Oh, that's probably why it wasn't, why that wasn't working too. Ah, sure. And reload changes, that's fine. Can I show you the, just give me 1 second, if you would. Let me do a debug. There's my debug. Can I see the assembly view on this? I can see the memory view of like result and so on, right? So I can see that. So that's that value in memory. And there's a really quick way to show the assembly version of it. I can't see it. I'll have to look. I'll find it and we'll see it later. You can see what the assembler code looks like for a given file. There's a view that shows you the assembly language code in case you want to go and tweak it. We'll do that on Thursday. All right, guys. Sorry, I'm a minute and a half over. I'll see you all on Thursday. We'll get office hours set up. That'll be job 1 for tomorrow. And otherwise, you have more questions, post them on Piazza. For serious stuff, we'll do one-on-ones with your CAs or your TF. All right, that's it. Bye, guys. Bye-bye. Bye-bye. You're welcome.